Hello everyone, and welcome to this fourth and last live session of the first International Electronic Conference on Chemical Sensors and Analytical Chemistry. This conference has been organized by MDPI and the MDPI journal Chemosensors, and it is chaired by Professor Nicole Jaffrezic-Renault from the Institute of Analytical Sciences in France. Thank you very much for joining us today. The conference is still open for discussion, so until July 15, you are invited to check and comment all the papers presented to the conference. You just need to go to the conference webpage. I would like to remind everyone that this live session is being recorded and that the recording will be posted in the conference webpage for everyone to watch it as soon as possible. Today we will also have a YouTube streaming, so I will share the link through the chat in a few moments, and you can share it among any interested colleague that can be interested to join us today. In the first part of today's session, we will have two keynote speakers presenting, and after then we will have a time for an open discussion. We will continue the webinar with three selected talks and a Q&A session during which we will address any questions submitted by the live online audience. If you are joining us live, I encourage you to type your questions in the QA box that you will find at the bottom of your screen at any time during the session. But it would be good if you put the name of the presenter which you are addressing the question. Finally, we will have Professor Nicole concluding the live session. This webinar will be chaired by our session chair, Dr. Tatiana Perova, from Trinity College Dublin in Ireland. Her main research interests are optical characterization of condensed matter with an emphasis on the analysis of the composition, stoichiometry, molecular orientation, stress and strain in amorphous solids, liquid crystals, photonic crystals, and semiconductors. Thank you, Tatiana, for accepting to chair this session. The floor is yours, and everyone enjoy the session.
Thank you, Anna, for presentation. And now we will start. We will starting from two keynote speakers, and the first talk entitled "One-Dimensional Metal Oxides: Growth and Strategies for Boosting Sensing Performance" will be given by Professor Elisabetta Comini. Professor Comini is the head of Sensors Laboratory at the Department of Information Engineering at the University of Brescia in Italy. She received her laureate degree in physics from University of Pisa in 1996. She then completed her PhD in material science at the University of Brescia in year 2000. Professor Comini's main research interest lies in the area of growth of metal oxides, namely nanowires and thin films, and investigation of their electronic, functional, and structural properties. Professor Comini has over 350 publications in peer-reviewed journals, books, chapters, and review papers, and she also is an editor of various books and holds 4 patents. So please, Elisabetta, you can go ahead.
Thank you very much, Tatiana, for your nice introduction. So today I will talk about our work on metal oxides, on the growth of metal oxides and how to boost their sensing, chemical sensing performances. We will see a little bit about chemical sensors, and then we will go into details with nanowires and heterostructure that we are able to prepare in our lab. And we will see how, we can improve the sensing properties, and we will try to draw some conclusions. So what is a gas chemical sensor? So This kind of sensor is a device that is able to convert the presence of chemical compound into something that we can read, such as, for example, the electrical resistance. So we have two different functions, the receptor and the transducer, the transducer function. So the first interact with the gas, with the target gas, and it absorbs, you can absorb on the surface, so you can have charge transfer, and then we have a transduction. So the conversion of this kind of reception to something that we can measure. And the way that we can transduce the signal is, for example, changing the change in electrical resistance, electrical conductivity, and this is what we will see today with our work on at the sensor lab. So this is the kind of device you can see here in the picture that we are using for this measurement. We are putting our material on the top of this substrate, putting contacts on the top and a heater on the back, and we are going to measure the resistance, the conductance over the time when we introduce the gases inside the chamber, test chamber that we are using. The advantages of this kind of conductometric gas sensor are that are many. I mean, the ease of fabrication, its simple operation, and its low production costs. Metal oxides are well known in this field for their reactivity and for their sensitivity to chemical compounds since from more than 50 years now. And normally, the most studied, that you can see here, are N-type semiconductor metal oxides. You can see here tin dioxide, zinc oxide, titanium oxide, tungsten oxide. While just a little bit, a few research work have been done on P-type metal oxide semiconductor. Metal oxides are really materials that can have very interesting properties, functional properties. Moreover, normally they can be produced in compact size, in easy ways, and also with low-cost experimental setup. And some of them are also abundant on the Earth crust. However, there are challenges that must be overcome if we want to have metal oxides chemical sensor with high selectivity, stability, high operation, low operation temperature, and sometimes they have high resistivity, which of course is something that increases the cost of the final device. And we need also to tackle the large scale production and the reliability of this kind of devices. And that's why we are working on materials. So how can we work, can we engineer our materials to improve sensing properties? And there are many ways, and some of them are doping, addition of metal oxides, the use of catalyst, functionalization of these materials, and also the preparation of heterostructures, so combination of different structures together. Nanowires and heterostructures are interesting because in the case of nanowires, we have well-defined crystal orientation, and we can have them single crystalline, so stable over long-term operation. And we can have also high surface to volume ratio. And it's easy to have nano-size dimension of these nanowires. Heterostructures, where we are having heterostructures, like in this image, for example, we are having surface enhancement, we can have grain refinement, and we can have charge separation, charge carrier separation. and increased accessibility of gases into the nanostructures. In our lab, in sensor lab, we are growing metal oxide heterostructure from different phases. So from a vapor phase and from a liquid phase. We are using vapor transport tubular furnace, vacuum chambers, thermal oxidation, but also hydrothermal method and electrochemical anodization. Today we will just see some of the preparation, few of the preparation techniques that we are using in the lab due to time constraints. We will focus ourselves on evaporation and condensation method that was discovered in the 60s, and it's a bottom-up technique. And you can use two different ways. So you can use the growth mechanism VLS, which is vapor liquid solid, where you have a metal catalyst, but during growth becomes liquid, and is a preferential condensation site for the vapor that you need to create in the furnace. On the other hand, you can also use the vapor solid growth, where you do not have metal catalyst required. The system is this one, and you can see you have a tubular furnace where you put in the higher temperature region your metal oxide powder, and in lower temperature region you put your substrate. You have a flow of normally inert carrier gas. We are using, for example, argon, and this flow is the mass transport from the source to the substrate. Of course, you need to select to find the right experimental parameters that can give you the one-dimensional grow instead of a particle or a film grow, which is the conventional one. So for each system, for each material, for each catalyst, you will find special, evaporation temperature, condensation temperature, and pressure of a system, since this system is kept at a pressure lower than the ambient pressure. Okay, so let's see some example of the nanostructure that we can produce. Here we see zinc oxide nanostructure using different catalysts. So here, platinum catalyst, copper catalyst, and silver catalyst. And you can see that the morphology, even if the substrates were at the same temperature, the catalyst influence the morphology. And even with the same catalyst, changing the condensation temperature, you can have different morphologies. So nanowires instead of nanorod. And it's really something that you need to experimental evaluate during your optimization of the growth process. We have investigated also tungsten oxide, and here you can see the morphology of tungsten oxide nanowires, which is, you see the diameter is really small, so from 10 to 15 nanometers. In this case, we have used gold catalyzed alumina substrate, and the temperature of the substrate is around 500 degrees C. And we are having this relatively long and small nanowires. We can see we have analyzed, of course, the structure and the phase of tungsten oxide that we have obtained. And we have seen that we have a monocrystalline, monoclinic crystalline phase of tungsten oxide, which is confirmed also from the Raman spectrum. We have studied also P-type oxides, since it's really interesting to have different behavior, because N-type and P-type semiconductor metal oxide respond in a different way when the chemical compounds are introduced into the test chamber. Also in the case of nickel oxide, the best catalyst for the growth has been gold. And it was difficult to achieve nanowire since the evaporation temperature of nickel oxide is really close to our limit of experimental setup, so 1,400 degrees C. And also the substrate temperature for the condensation is very high, as you can see here, 900, more than 900 degrees C. And but at the end we were able to achieve this nanowires morphology. The diameter of the nanowires is from 15 to 60 nanometer. And if we have a look at the crystalline phase of nickel oxide, we can see that is the Bunsenate structure, which is also, I mean, the presence of nickel oxide is confirmed also by Raman measurements. Then we have tried also to prepare other P-type material like bismuth oxide, which is not so used as a gas sensor material. And even in this case, the best catalyst was gold. And we can see here the morphology of these nanowires, and we can see that in this case the diameter is much higher compared to the other oxide. Then we have a diameter around 100 nanometer and a very long length, 6 micron in length. While we can see that at the top of the nanowire we have still the presence of the gold catalyst. You can also see here the EDX spectra, where we can see that the tip of the nanowire is gold, while we have bismuth oxide in the upper part. We have the alpha phase of bismuth oxide, and we can see also the crystalline phase of gold at the top of the nanowires. So now let's see what we are doing with this metal oxide. We are preparing our, the nanowires on our transducer, on mini transducer, and we are putting contacts and heater because we need to heat our metal oxides to have a reliable and fast reaction with the environment. Then we are putting them in our test chamber where we can put up to 10 sensors and we can control the environment in terms of the presence of chemical compounds and humidity. What's happening when we have the interaction of, we are heating our metal oxide and we interact with the oxygen that we have in the atmosphere. We have the absorption of oxygen on the surface and we have the depletion of electrons that are reacting with oxygen and are trapped with oxygen. So in this region, we have a depletion of electrons if we are talking about an N-type semiconductor. And when CO, for example, comes, interacts with oxygen adsorbed and release these the same electrons. So we are measuring the resistance, the conductance, and if you are measuring the conductance and CO comes, we see an increase in conductance for N-type metal oxide, where we are seeing a decrease in conductance where we are measuring P-type semiconductors. So here we can see the functional characterization of bismuth oxide. And we have tested the acetone and ethanol. And we can see that as the gas is introduced, we have a decrease in conductance and then back again to the previous value when the airflow is restored. We can see that we have a very high response, measured as the relative variation of the conductance over the baseline conductance as 10 ppm or 40 ppm of acetone and ethanol are introduced in the test chamber. And this response changing as a function of the evaporating temperature. We can see that we have a maximum around 350. And if we have a look at the calibration curve that are the response over concentration, we can see that it follows a power law, which is typical for metal oxides. And it depends, of course, of the chemical compounds that we are testing. And we have also tried how the response is influenced by the humidity. So this is the response of bismuth oxide nanowires towards 2 ppm of acetone over different value of humidity from 50 to 90%. And we can see that the variation in percentage is relatively low. So we have also tested other compounds to see the selectivity of bismuth oxide nanowires. And we can see here that the highest response is towards ethanol and acetone, while the other compounds has very lower responses. So the problem is that, as you have seen, that we have no perfect selectivity over different compounds. And this is also one of the reasons why we are trying to have different materials and different heterostructure to try to improve these properties of metal oxide chemical sensors. In terms of heterostructure, we can have different, very different morphology. We can have branching heterostructure, like in this case that we are investigating with the combination of nickel oxide and zinc oxide. So first we are growing nickel oxide heterostructure using gold catalyst, and then we are growing on the top of it zinc oxide heterostructure with no catalyst except the one that is present on the nickel oxide one. And we can see here very nice structures. Well, the core is the nickel and nickel oxide, and the arms are the zinc oxide. What we have seen is that we have an epitaxial growth of zinc oxide over nickel oxide, also thanks to the very limited interface that we have between nickel and zinc oxide. When we are going to see the functional behavior of this heterostructure, we can see that the response of nickel oxide, of course, is a p-type semiconductor. So as we introduce ethanol and acetone, we have a decreasing conductance. While in the heterostructure-based sensors, we have an n-type semiconductor behavior. So we have an increase of the response. And if we compare the response over the temperature to acetone and ethanol for the nickel oxide and from the heterostructure, we can see that we have an enhancement in the response toward these volatile organic compounds in the case of heterostructure itself. Of course, we can try the combination of many and many materials, and this is what we are doing. And we have tried to grow tungsten oxide on the top of nickel oxide. In this case, the situation, the morphology is really different. You can see here, we have very long growth of tungsten oxide over nickel oxide. And we have also a ternary compound, a nickel tungstenate that is formed in between the junction of these two materials. Even the functional properties are much different. If you can see here the conductance over time when we introduce ethanol and acetone, we can see that the behavior of heterostructure this time is a p-type behavior. So we have a decreasing conductance when we are introducing the volatile organic compounds. And if you can see the response over the response over the temperature, we can see that we have, or even in this case, an enhancement and decrease in the detection limit of ethanol and acetone compared to nickel oxide, pure nickel oxide. But this is not the only way where we can do heterostructure. We can also have core shell heterostructure, and this was done in cooperation with the Amall University of Berlin, a group of Nicola Pina. And we gave him our tin oxide nanowires, and they covered with a small layer of nickel oxide on the top. what we can see is that we have a decrease in the baseline conductance as we increase the thickness of this nickel oxide layer. And we have the junction formation at the interface. And we have an optimal working temperature very high, which is 500 degrees C. And if we see the response of towards hydrogen of this layer, we can see that we have an increase compared to the bare tin dioxide material. In order to conclude, I would like to say that we have shown different metal oxides, and I hope I was able to show you that different materials have different performances and different response spectra to different chemical compounds. So the morphology influences the performances, but not just the morphology. Also, the preparation method is influencing the performances. So the way you're preparing your material changes the response spectra of the material itself. This is why it's really crucial to study in deep the preparation procedure and to be able to reproduce the material and the procedure in the same way in order to have the same functional performances, which is a key factor in if we would like to have a real device that can be used in real application. So we have measured the performances of both binary metal oxide and also heterostructure. And we have seen that in the case of the combination of different materials, so with the heterostructure, we have an optimization of the sensing performances, at least in the case that we were studying. And we have seen that we have very nice functional performances, and we hope that this will help to create to improve the chemical sensor technology, which is something that really can help the society, our society, to create new lifestyle and to help to go towards a sustainable growth of our society. Because, of course, we know that it's important to monitor the presence of chemical compound in our environment, in indoor environment, in industry, and also in the food field, to monitor what is happening during the preparation of food, but also during the transformation, and also when we are having this food back in our hands. So nanotechnology is something that can help is kind of the production of a reliable sensor, and maybe it has been overestimated, but I guess in long term we will have a great implication of nanotechnology on healthcare, on productivity, and also on the environment. Metal oxides are in one of the most promising class of materials, and also thanks to their chemical stability and to the easy fabrication of this material. We were one of the first to be commercialized in form of thick films for conductometric chemical sensor, and I'm sure that they will be part of the future of chemical sensors in different forms. I would like to acknowledge the project that we're supporting this kind of research. So an Italian project, and also NATO Science for Peace and Security programmer underground, which is advanced electro-optical chemical sensors. And of course, you for your kind invitation. Thank you very much.
Thank you, Elisabetta, for very interesting presentation. And I just would like to note again to everyone that this talk and the next talk will be open for discussion from 10 to 10:20, when the second keynote talk would be given. And then we will discuss both presentation. And please put your questions to the special place called questions and answer. You can write your question, and please indicate to whom particular your question is addressed. So thank you, Elisabetta, and we will discuss at 10 o'clock. Thank you. So now we are going to the second talk entitled Electrolyte Gated Field Effect Transistors for Monitoring Photosynthetic Activity. And this talk would be given by Professor Benoît Piro. And Professor Piro is a full professor in the Laboratory of Smart Surfaces at the Department of Chemistry at Diderot University in Paris. And he has more than 130 publications with nearly 4,000 citations. Professor Piro has developed various types of electrochemical biosensor directed to target molecules such as microRNA, proteins, peptides, antibodies, organic pollutants, and many others through several collaborations with biotech company. He's also working on development of organic electronic devices, such as organic field effect transistors, namely electrolyte gated organic field effect transistors and the graphene field effect transistors. And probably some of these would be mentioned during his talk. So Professor Piro, you are welcome for your presentation.
Thank you very much, Tatiana, for this kind and complete introduction. I hope that everyone can see my screen properly. So yes, I will focus today on the way to use the electrolyte gate field effect transistors for monitoring the photosynthetic activity of some living organisms. Work done in the group BIOS, Bioelectronics and Smart Surfaces, belonging to the laboratory ITODIS, itself belonging to the University of Paris now. It's no more Paris Diderot, but University of Paris. My name is Benoît Piro, and thank you for being here. Well, I can switch to the next. Yeah. So first of all, I'd like to probably it's necessary to go back to the functioning of field effect transistors and transistors in general. Start with the organic field effect transistors or FETs. Organic because the semiconductor is organic, usually polymer or oligomers. And field effect transistor because there is a field effect between a gate, sorry, it's in French here, the gate, and the semiconductor through a dielectric. And below that, in this bottom contact case, two electrical contacts, the source and the drain. And depending on the potential at which the gate is put, a current, well, a channel, will be created by charges, say charge carriers, accumulated through the electric field. Here at the interface, actually, here in between source and drain, and then we can adjust the conductivity of the channel and then adjust the current flowing through the source and drain contacts. This are two examples, yes, of an output curve, that is the drain current as a function of the drain voltage, and here of a transfer curve with the drain current, or square root of it, as a function of the gate voltage. So we can vary the drain current by adjusting or varying the gate voltage that way. Well, for the purpose of sensing, these organic field effect transistors are not always very convenient. That's why ion-sensitive organic field effect transistors or ion-sensitive field effect transistors have been developed. The structure is very similar, but in electrolyte, could be water, is added in between the gate and the dielectric. So that if the dielectric is, for example, functionalized with an ionophore, or simply could be protonated, depending on the pH of the electrolyte, then not only the electric field in between the gate and the semiconductor due to the gate voltage is present, but also an electric field or a potential drop due to the accumulation of charges at the interface, typically here at the electrolyte dielectric interface. So for this easy example, due to accumulation of protons at this interface, we can see a change in the transfer curve. When I say change, it's generally a shift of that transfer curve, that is of the gate voltage seen or sensed by the sensor, by the transistor. And so we could amplify, because it's an amplificator, amplify a tiny voltage change, which follows the Nernst equation, by a large, depending on the slope of these curves, a large current change. That's the principle. There are also organic electrochemical transistors, or ECTs. Again, the structure is very similar, but in that case, the dielectric is suppressed so that the semiconductor is in direct contact with the electrolyte. But in this case, the semiconductor must be electroactive and is typically p-doped by polystyrene sulfonate, PSS. I will not give example of that because I want to go directly to the water gate organic field effect transistor, or electrolyte gated, E instead of W, okay, organic field effect transistor, the structure of which being absolutely similar to that of the OECT, but in that case, the semiconductor must not be electroactive. Is not, even if in direct contact with the electrolyte, and is selected to behave as a true organic semiconductor, typically P3HT, DPP-DTT, or many others, which are stable in contact with water and stable with time, stable in contact with oxygen as well, and not electroactive again. So if they are not electroactive, that is, if there is no ions going through the semiconductor, upon application of a gate voltage between the gate and the source, and between the gate and the semiconductor, charged, that is ions from the electrolyte, will accumulate at the interface gate electrolyte and at the semiconductor electrolyte interface, forming the very well-known double layers, of course. Okay, but the capacitance of which being very large, the potential drop at the interface, at the gate electrolyte and interelectrolyte channel interface, are usually very large in this configuration, so that they can work at very low voltages, around 1 volt, or even a few hundreds of millivolts instead of several tens of volts for more classical transistors. If I illustrate the functioning with no gate voltage applied there is no current, and when the gate voltage increases, then the current increases progressively through the channel between source and drain. And this is really related, directly related to the capacitance of the device. See here. That way, first I could say that these kind of devices are relatively easy to fabricate by conventional microfabrication protocols, strategies on silicon wafer, for example. Semiconductors are available even commercially, and we can adjust the size of the component of these transistors and typically adjust the area between the gate and the semiconductor area, and it makes device relatively different in that sense that if the gate is, say, large compared to the area of the semiconductor, then the polarization, the voltage drop at the gate is going to be minimal, and the voltage drop at the electrolyte semiconductor will be maximum. On the contrary, if the gate is small, then most of the potential drop between the gate and the semiconductor is well described. If we use large gate electrodes, say microelectrodes as gate, we could use naturally, would say, the electrolyte channel interface and functionalize that electrolyte channel interface, say with antibodies, antigens, DNA, or whatever, to sense a binding typically. This is an example, but again, I will not take too much time on this because I would like to switch to another application. But it's possible, and it has been well described now, that it's possible to functionalize the channel interface to sense some tiny changes at the interface with the electrolyte, with these devices, and amplify the change into a current, of course. Well, and if let's say again that, as I already explained, that if now you switch to microelectrodes with a tiny gate compared to the area of the semiconductor, then considering that the overall capacitance is actually, the reciprocal capacitance is the sum of the reciprocal capacitance of each interface. If the gate is small compared to the area of the semiconductor, then the 1 over this capacitance of the semiconductor could be neglected. Then the only capacitance to take into account is that of the gate of the gate, I say. Okay, and then we will focus on the functionalization of the gate. Now, it's illustrated here. If we vary the gate area, we can measure a change, all other parameters being constant. We can measure a large change of the drain current that way. And this is due to that reciprocal relation giving the capacitance, the overall capacitance of the device. So then, of course, for large gate, the current is maximum, of course. I will come back on that later. And also, we could see that if the area of the gate is changed, if the size of the gate is changed, it has also an influence on the threshold voltage, that is voltage at which the current start to significantly increases through the device. We also, I can continue with that. If we follow the with a reference electrode, typically dipping in the electrolyte, if we try to follow the voltages at each interface compared to that of, compared to the reference electrode, of course, we could see that for large gate, the potential of the what the potential drop at the interface between the semiconductor and the electrolyte follow largely that of the gate. But if we reduce the size of the gate, that is not the case anymore, because there is I would say a switch from most of the voltage drop at the gate to most of the voltage drop at the semiconductor interface. So we play with that. We put that into equation, of course, but I will not spend time on that now. The interesting behavior that we have seen is that gate voltage, or the effective or efficient gate voltage, can also be changed if we make a redox reaction at the gate. That is, if the gate is able to oxidize or reduce something which is present in the electrolyte of the transistor. And in doing so, then there is a change, actually a decrease of that delta VGE at the interface, and then most of the voltage drop occurs then at the semiconductor interface, so that the current flowing on the gate, which is usually a drawback in every transistors, in that case, the tiny current flowing at the gate of the transistor is transduced, amplified into a quite large drain current flowing through the transistor. We also check that the transistor characteristics depend on the gate material. Could be titanium, it could be even sorry, well, I forgot, but it could be titanium, it could be gold, it could be platinum. It works with the gold gate quite well. Here are the transfer characteristics for an Igor FET using a gold wire as gate, and here is the characteristic with a platinum gate. So it's similar, even if, because the capacitance of the gate is slightly higher than that of platinum, I mean, slightly higher in water than that of gold. The current is higher using the platinum gate, all the parameters being constant, and the voltage, threshold voltage, is slightly shifted. We already tried to explain this phenomenon in some publications. What is interesting here is that we could use the platinum gate as a catalytic electrode, catalytic gate, and, for example, monitor the electroreduction of oxygen, dissolved oxygen in the electrolyte, by putting the gate as a convenient potential. Negative potential here, because we use a p-type semiconductor, so the transistor works in p-type and then in the negative quarter of the gate. Here is just to show you that, depending, of course, on the gate voltage, change here in red, in electrolyte without oxygen, then in red with some oxygen, and in blue with saturated oxygen, the current start to flow through the drain, and start also to flow through the gate, of course, but I didn't show the gate current. As soon as we start to reduce oxygen on the gate, and there is an amplification factor, that is the ratio between the drain current and the gate current, which is, well, I would say constant, of around more than 100. It could be 170 here, up to 1000, actually, depending on the geometry of the device. So we could amplify that redox reaction, oxygen reduction, through the device. That's what we did here, again, by switching from argon degassed solution, argon degassed electrolyte, to oxygen bubbled electrolyte. And you can see that when there is no oxygen, there is little current at the gate is in red here, and little current at the drain. Please keep in mind that the gate current are expressed in nanoamps. The drain current is expressed in microamp, okay? So it's not the same scale. And you can see that the drain current follows with high fidelity, let's say, the gate current, depending on the presence or not of oxygen in the medium. Okay. So we try to apply that to the monitoring of photosynthetic organisms. Here we did that on cyanobacteria and Abainaflux aquae, but it could be done on any kind of living, of course, photosynthetic organisms that we put directly here in that first example in the electrolyte within the electrolyte compartment of the device. So it makes a kind of green transistor. And we follow under light and dark alternance. We follow the production of oxygen by the cyanobacteria, which is really active. And again, it's not the same scales. The gate currents are expressed on the left-hand side scale here, relative intensity compared to the maximum. And the drain current is expressed here on the right-hand side scale. It's not the same scale at all, okay? It's largely amplified. But what is interesting and clear is that the drain current follows the light and dark cycles and follow the current, reduction current occurring at the gate, depending on the production or not of oxygen by the cyanobacteria. So it works very well. We did the test without cyanobacteria to see that, yes, there is some very little photocurrent, which is expected, of course, but it's very small compared to the current due to the amplification of that tiny gate current. So, well, yeah, it also depends on the quantity of cyanobacteria in the medium, of course. So it's clear the behavior of the device is due to the activity, photosynthetic activity of the cyanobacteria. So we decided to make that device more usable, let's say, by immobilizing these cyanobacteria directly on the gate of the device and not within the whole electrolytic compartment. For doing so, we immobilize the cyanobacteria in an alginate hydrogel that we, so it's really nice, it makes it like a chlorophyll gum, I would say, and immobilize that on the gate by first electrografting ethylene diamine, sorry, on the platinum gate, and due to electrostatic interaction with the alginate, it helps to immobilize the hydrogel on the gate, on the platinum gate. Well, the platinum is a very tiny tip here, okay, of 100 micrometer here in diameter. And we follow that way with this new device, sorry for the French, night and day alternance, simulated here with a LED lamp. And again, we saw a nice fidelity, the drain current following the gate current, the high fidelity, and a large, nearly 1000, if I remember well, larger amplification between drain and gate. Okay, so we could use that device, for example, just an example and preliminary results, but for checking the cleanliness of surface waters into which cyanobacteria, for example, are living or are put. Here is the alternance, well, the drain current upon alternance of dark and light in a clean electrolyte without any pollutant. And then after addition of glyphosate or diuron, which are known to kill or at least inhibit the activity, photosynthetic activity of this cyanobacteria. And indeed, after say 30 minutes incubation with 10 micromole glyphosate or diuron, we saw a clear decrease up to zero, down to zero after a given time, clear decrease of the activity of the cyanobacteria, and then a clear decrease of the drain current. I have 5 minutes, so I will continue on the fact that we also try to use, and we did actually, graphene to make such kind of electrolyte gated graphene field effect transistor to try to improve the stability, because if I say that organic semiconductors could be stable in water, it is true for some time. But if we would to make the device very stable for a long time, several days or weeks, then at least for the moment, organic semiconductors are limited. So we switch to, or we try to use graphene. And because graphene is not easy to process, we use graphene oxide and even a graphene oxide ink that we inkjet print. So we needed to engineer that ink, but we succeeded to inkjet print graphene oxide ink, stable, homogeneous, etc., on our interdigitated source and drain device, the transistor. There are some pictures, but I have no time to discuss on that, but just to show that it's not, of course, a single layer graphene, it's several layers. On top of it, it's quite homogeneous. And then, because graphene oxide is not conductive and not interesting, we electroreduce graphene oxide in situ on the transistor by short-circuiting the source and drain contact and apply a reduction potential. Then the graphene oxide becomes darker and darker depending on the yield of reduction. What is interesting actually is if graphene has a direct point, that is the point of minimal current between the whole transport side and the electron transport side, reduced graphene oxide has a direct point which is quite far from the 0 volt gate voltage because of residual doping. And actually that electrochemical reduction allowed to select our level of reduction depending on the charge passed through the transistor, through the reduced graphene oxide, or time of reduction. Okay, so we can adjust the position of the direct point that way, and adjust actually. You see where are the whole branch or the electron branch of the device, of the characteristics. And that way, we try to, by adjusting conveniently the position of that direct point, we try to use the device as well for sensing oxygen reduction on the gate. I have not really time to go into details, and it's not the main part of the job here, but it works in the whole section at gate voltage far from here in the negative domain, and we were able also to follow the change in gate current following the drain current following the gate current. That time, because reduced graphene oxide is much more conductive than an organic semiconductor, we're able to amplify the gate current by a factor of 1 million, 10 to the power 6. And it worked as well for detection of diuron, in that case, with a smaller concentrations. So, in conclusion, I wanted to show you that electrolyte gated field effect transistors, which have low operating potentials, work in biological conditions and can be used to detect change at the semiconductor electrolyte interface, but also at the gate electrolyte interface. And may also, and it's more surprising, actually, are able to follow redox reactions at the gate. That way, we were able to follow the oxygen production and then reduction, electroreduction at the gate, oxygen production by photosynthetic organism, put immobilized on the gate or directly present in the electrolyte medium. We're also able to make this device by inkjet printing, typically for the graphene oxide device. I have no time for the perspective, so I switched directly to the recent picture of the BIOS, Bioelectronic and Smart Surface group in Paris, and I thank you very much for your kind attention.
Thank you very much for your very interesting presentation. And now I think both talks are open for discussion. And let me first ask you a simple question. I noticed that you mainly were working on 2-inch silicon wafer to produce your field effect transistor devices. So is it, what's the main limitation for increase the number of devices produced on one wafer? Is it just like university laboratory condition or anything?
Sure. Many things, I would say. Of course, university conditions, we work usually on 2-inch wafers. It could be possible to work on large wafers. Actually, what we are developing for the moment is the inkjet printing process to try stop using clean room technology, which are very costly, and try to print our device not on paper, even if it's possible, but to print on plastic sheets. To answer it, so it's one part of my answer. Is of course university limitation, but we are trying to go beyond that and try to make this device by or maybe more accessible ways, even for industrials, of course. And to directly answer your question, size, well, we could reduce the size of the device as well. Okay. Here I show you a relatively large device of say 2 millimeters in size. But well, we could make a much smaller device, but in this case, the current is going to be smaller. Yeah. That's also the reason why graphene could be interesting, because if you crunch the design to very, very teeny device with an organic semiconductor, the current is going to be very, very small. Okay,
good. Thank you. I can see only one question now, which address, I think, to Elisabetta from our auditorium. And the question is from Racine Alontio. And the question is, which precursor are you using for growth nanowire in the tubular furnace?
We are using the oxide itself, so an oxide powder. If we are using, for example, if we want to deposit zinc oxide, we are using zinc oxide powder. So we don't have chemical reactions between precursor, but we are using the powder of oxide itself. So we are evaporating the powder, and then it condenses in a different region, in different thermodynamic conditions. And this is the reason why we have one-dimensional morphology.
Okay. So just one question from me related to your talk. Yeah. I believe that using heterostructure, you obtain much larger surface area, like as I can see from SAM images. So it looks like very large surface area. So what about like performance of these particular sensors? Would be this much better, or of course they're specific for specific application, but just wondering about what the performance of this.
Yeah, I mean, this is one of the reasons that we are using heterostructures, and because we are able to have a higher surface to volume ratio, and this is a peculiar, a key thing in preparing chemical sensors, since all these kind of functional application are really strictly related to the surface and to the ratio of the surface volume ratio. So you enhance the surface exposed to the environment, and this is not the only reason, let's say, because with having a heterostructure of different metal oxides or different materials, because you can also combine a metal oxide with other kind of materials, you are having the possibility of changing the reaction, and also maybe use one of the metal oxide as a receptor and the other metal oxide as a transduction material. So this is something that you need at the end to study in each kind of selection that you are doing with the heterostructure. As I show you, we had very different behavior when we are combining nickel oxide with zinc oxide and with tungsten oxide. And this is also for our combination, for the use of different morphology, like functionalization with catalyst on the top. And it's really, unfortunately, something that you need to try from the experimental side at first, because there's not that much a study on theoretical study that can predict such behavior at the end. So it's really something that you need to study case by case, unfortunately.
Okay, thank you very much. Also, I can see that now there is also a question back from Racine. So she's writing that, so for a mixed metal oxide nanowires, it is possible to move from a mixed powder sample as a precursor, or you always need to grow it step by step?
Yeah.
So one oxide and then another.
And then another one. Yes, if you are really looking for having a heterostructure like the one that I showed, so one core, one basal structure, and something that grows on this, then it's better to do a two-step grow. When you are mixing powder, you have both the oxides in the vapor phase. And so if you're not, if depending of course on the percentage that you put in your source powder, but many times you are going to obtain doping or segregation of different structures. So not what you would like to have a heterostructure itself, but again, it depends on the two oxide that you're using. So I cannot tell a rule for it. I mean, I cannot tell just what is on our experience.
Okay, thank you very much. So now again, the question is from Nicole and to Elisabetta, and it's the question is, can you comment on the recyclability of these nanomaterials which you use in your presentation?
Yeah, I mean, recyclability is something that normally is not taking into consideration, let's say. What I can tell is that some of the metal oxide that we are preparing are, let's say, can also be are not dangerous to humans. in order to recycle the small amount, which is good, it is a really small amount that we are using. So the substrate, I didn't told you maybe, but it's a 2 by 2 millimeter, and we are depositing just some hundreds of micron of our materials. And the problem is that it's not just the metal oxide itself, which maybe could be removed from the substrate. The fact is that you have together the oxide, the platinum, the contacts. So in order to recycle, really recycle the material, you should have first a separation of these parts that compose the sensor itself. So I do not see here very easily. I mean, it should be much expensive to recycle. The good thing is that they are very small, so it's not a high amount of material that you are using. They are not even a film; they are nanowires. So yes, maybe they can be also several micron long, but most of the space is empty. I mean, not all the space is occupied by the nanowires in these microns of thickness.
Yeah, good. Thank you very much. Now, I don't see any more question. I have some small question to Benoît. When you were talking about graphene oxide, how many layers of graphene in this case would be useful for the best device performance?
Oh, it could be very interesting to work with only one layer, of course, but if the device is made by inkjet printing, it's not at all the case. We measure a thickness of around, say, 20 to 30 nanometer. Okay, so it's a thick layer of disorganized reduced graphene oxide. So tell you which thickness is the best for you, for me, is maybe difficult to say.
Right. Okay. Thank you very much. So, yeah, there is a question, I think. Yeah, again to Elisabetta from Giuseppe Capelli. It's
Capelletti, yes.
Yeah. Unfortunately, there is no end of this. So anyway, the question is, one of the main challenge in room temperature detection. Did you obtain results about this particular point?
Yes, we, of course, I mean, in this 30 minutes talk, I had to choose something to show. So I didn't show anything concerning this, but we were working also on room temperature sensing, which of course is one of the best, result that you can achieve with metal oxides. In particular, we were combining we are doing two things. I mean, functionalization with structures like graphene oxide, reduced graphene oxide, and also the use of optical enhancement. So of the use of light, ultraviolet light, to enhance the response of this kind of materials. And the results, I mean, we have achieved were good in the case of nitrogen dioxide and on some volatile organic compounds. So, of course, the dynamics is still not so fast as we are having with when we are operating at several hundreds of degrees. But at least we have a good response towards this compound using these two tricks, let's say, the use of light in order to enhance the response instead of using the temperature.
Okay, thank you very much. So now a question to Benoît again from Nicole. And Benoît, do you need to use a reference electrode for the polarization of the gate?
no need, even if it's possible. So you can, when you don't know well your device, you can use a reference electrode indeed. But most of the case, we don't.
Okay. Yeah, unfortunately, I don't have any more questions. So thank you very much. Again, only I can see some comments. Thank you both for very interesting talks. And so it's really useful for practical applications, and it's very nice. So now we're moving to the shorter presentation, and the first presentation would be given by Anna Carolina Afonso, and she will present the talk on carbon dots as a fluorescence pH nanosensor by application of an active surface preservation strategy. So you are welcome.
Thank you.
Presentation.
Good morning. I'm Anna Carolina Afonso. I am a chemistry master's student at the Faculty of Sciences of the University of Porto, and I'm here presenting my work about carbon dots as a fluorescence pH nanosensor by application of an active surface preservation strategy. The monitorization of pH has a significant role in various environmental, industrial, and biomedical applications, and despite glass pH electrodes being the most used type of pH sensor, their size and invasive nature limits their application in low-volume samples and in cellular pH sensing. Fluorescence-based sensors do not present such limitations and are able to provide a non-invasive solution. One way for the development of fluorescence pH sensors is through the use of carbon dots. Carbon dots are carbon-based fluorescent nanoparticles with valuable properties such as high photoluminescence, high aqueous solubility, low cost, low toxicity, and good biocompatibility. The application of carbon dots as pH nanosensors has been studied before. However, there are still issues in the current level of development of carbon dot-based pH sensors. Due to the lack of knowledge regarding the mechanism that governs carbon dots' response toward different analytes, there's a need for complex post-synthesis functionalizations. The pH ranges to which carbon dots are responsive tend to be limited, and oftentimes, while being responsive to pH, these carbon dots also tend to respond to the presence of interference not being selective toward pH variation. Given this, our aim in this work was to use the active surface preservation strategy to rationally develop a carbon dot-based nanosensor with controllable sensing properties. This strategy allows the carbon dots to retain the structural features of the precursors on their surface, making these nanoparticles retain their properties without post-synthesis functionalization. To be more specific, a carbon dot-based nanosensor for pH sensing was developed as proof of concept via the active surface preservation strategy by employing fluorescein as one of the precursors, along with citric acid and urea via a one-pot hydrothermal treatment. Fluorescein was used since it is a commonly used fluorophore and was one of the first studied pH sensors. To understand the role of fluorescein as a precursor and the success of the employed ASP strategy, besides preparing carbon dots coated with fluorescein, another type of carbon dot was prepared, which consists of an identical procedure but excludes fluorescein from the synthesis. Here we have representative higher resolution TEM images of both synthesized carbon nanoparticles, the first being of carbon dots without fluorescein, showing them well dispersed in an aqueous solution where you can observe a carbonaceous amorphous structure with a mean diameter of 2.5 nanometers. On the other hand, when carbon dots are coated with fluorescein, they aggregated, maintaining a size of 27 nanometers and the regular spherical aspect of carbon dots. The surface composition of these carbon dots was characterized by XPS analysis, where the carbon dot with fluorescein showed a chemical surface composition of 77% carbon, 3% nitrogen, and 17% oxygen, and by comparing both spectra, the presence of a pi-to-pi contribution in the carbon dot with fluorescein spectra, which is absent in the carbon dots without it, indicates the presence of fluorescein-like structures in the surface of the nanoparticle. We also evaluated the carbon dots' optical properties, and the UV spectrum of fluorescein of both carbon dots was analyzed at 3 different pH values. In the spectra of fluorescein, we found an absorption band at around 440 nanometers at acidic pH, which then redshifts up to around 490 nanometers with increase in pH. In the case of the carbon dot with fluorescein, while absent at pH 3.24, a small band is formed at around 500 nanometers at basic pH, and the intensity of this band appears to increase with pH. We attribute this band and its pH response to fluorescein-like structures in the surface of the carbon dot. On the other hand, the UV spectra of the carbon dots without fluorescein does not present neither a band at around 500 nanometers nor a pH-sensitive response in this region of the spectrum. The fluorescence wavelength maximum of the carbon dot with fluorescein was 525 nanometers, which is similar to standard emission profiles of fluorescein. And furthermore, as seen for fluorescein, the carbon dot undergoes significant fluorescence enhancement with increasing pH. This data was then fitted with a logistic function with a correlation factor of 0.994 within a wide range of pH values from 3.7 to 12. As pH sensors require good stability and selectivity, we performed an array of tests, starting with a photostability assay of the carbon dot in acidic and basic pH, where it showed itself to be photostable under visible light irradiation. The effect of the ionic strength on its fluorescence intensity was also evaluated by preparing a series of solutions with different ionic strengths, and the increase of potassium chloride showed no appreciable effect on the signal intensity of the carbon dot. We also investigated the potential interference of different species toward the fluorescence signal of the carbon dot in aqueous solution, where no relevant change was seen in the presence of either interference. And finally, the pH reversibility of the fluorescence emission of the carbon dot was tested by adding the carbon dot to a buffer solution of 3.7 and repeatedly switching the pH between 3.7 and 12. There was a reproducible reversibility of the carbon dot's fluorescence signal with pH variations, despite a slight decrease in the fluorescence intensity at basic pH. Overall, the carbon dot coated with fluorescein showed itself to be highly stable. To further validate the suitability of this carbon dot as a fluorescence pH nanosensor, we used it to determine the pH values of 2 real water samples by applying the previously shown logistic fit. The results show that pH values obtained with the carbon dot agree with those obtained with a standard pH electrode-based method, and so validates its use as a fluorescence pH sensor. We also assessed its biocompatibility by adding the carbon dot to human cells in increasing concentration for 48 hours, and the cell viability was determined via an MTT viability assay. There was no significant drop in cellular viability. Thus, our results indicate that the carbon dot is indeed compatible with human cells, and so can be of potential use for intercellular pH measurements in biological applications. To sum everything up, a fluorescence pH nanosensor was rationally developed by using an active surface preservation strategy. The carbon dot can be used to determine pH values from 3.7 to 12 by fluorescence enhancement at 525 nanometers, showing also pH selectivity, reversibility, and photostability, while being compatible with human cells. Therefore, the fluorescein-coated carbon dots show potential for intercellular pH determination. More importantly, our work demonstrates a strategy in which carbon dot-based nanosensors can be rationally developed without requiring time-consuming and costly post-synthesis functionalization procedures. I would like to end by thanking everyone involved with this project, to thank the organization for the opportunity to be here today, and thank you to everyone watching for your attention.
Thank you, Anna, for very nice presentation. Because we have some few minutes time, I would like to ask you a question. I maybe missed this point, but is any effect of carbon dots size and shape on fluorescence position or intensity, or this was not investigated?
You're asking if the size had an effect on the fluorescent intensity? Is that?
Yeah.
It would be hard to tell as there was not really an investigation as if the size would have an effect, because we only analyzed the carbon dots with fluorescein and without it.
Yeah.
And without it, of course, there is a drop in fluorescence and in the size.
Yeah.
So adding fluorescein definitely adds to the size of the carbon dot and enhances its fluorescent intensity and pH response, obviously. But I'm not quite sure if the size would be the reason for this increase. So I'm not sure if I'm quite able to answer your question.
Yeah, no, it's fine. But did you do, do you know the size of carbon dots which was used in your case?
Yes, carbon dots are usually between 0 to 10 nanometers. In our case, it has around 27 nanometers, which is a bit higher, but it's still in the nanoparticle area. And we still don't quite know because they aggregated, giving it this size of 27. But
okay.
Yeah, it's around 27 nanometers.
Okay. Thank you very much. And thank you. Just 1 second, maybe. Yes, there is a question for you from Carlos Enrique Torrens Mendes. The question is there a covalent bond between the carbon dot and the fluorescein, or is absorbed only?
Yeah, yes, it's by covalent. It's probably, I can't say for sure, due to the formation of the carbon dot. But yeah, in principle, the fluorescein would be connected to the main core via covalent bonds.
Okay. So there are no questions. Yeah, if any questions will arise, then we have open discussion after 2 other talks will be given. So thank you very much again for a very nice presentation. And now we are moving to our second talk in this short session. So this talk will be given by Miguel Prieto. And the title of the talk is Essential Oils as Possible Candidates to be Included in Active Packaging Systems and the Use of Sensors to Monitor the Quality of Foodstuff. So is Miguel Prieto ready for a presentation?
Good morning. It will actually be me, Dr. Tatiana, Márcio Caracho. So good morning. Thank you very much for the invitation to be here today. My name is Márcio Caracho. I come from the Centro de Investigação de Montanha, from the Polytechnic Institute of Bragança in Portugal. And part of this work was also done and performed in the University of Vigo in Spain. So today I'm going to talk a little bit about essential oils and how they can be used in active packaging systems. Before I start speaking about the essential oils, I'm just going to give a little introduction on active packaging. So active packaging has to establish an interaction between the food and the package itself, and they are used basically for as a preserving function of food. So some examples are CO2 scavengers or emitters, as we can see here in the coffee bag, because coffee beans after roasting emits carbon dioxide, and it has to be removed from the packaging so there is not a buildup of carbon dioxide. There are also oxygen scavengers, which remove oxygen, which is an oxidizer, from the packagings. There are moisture absorbents that remove moisture from packaging, and some of the most important active packagings are ethylene scavengers. So, as you know, fruits, while ripening, they emit ethylene, and this ethylene, as it builds up inside a package, for example, will promote a very fast ripening of fruit and lead to them becoming rotten. So removing ethylene will actually reduce the rate of ripening of fruit. So this is active packaging, when the actual package has to interact with the food to have some effect. Essential oils or metabolites that are produced in the secondary metabolism of plants, they have quite a lot of antioxidant and antimicrobial and other properties, but here we are working with these two properties, antioxidant and antimicrobial. Although they are not used in the European Union as food additives, widely used, this is, in the United States, they are already classified as GRAS, meaning they are generally regarded as safe. So we expect in the near future that essential oils will start to be used in foods, in preserving foods. Recently, there has been quite a lot of demand for natural additives in the food industry, a demand for food additives that are natural based, but also a more green and more sustainable conscience in terms of packaging. So both the packaging and the way that food is preserved or sweetened, consumers tend to ask for natural based molecules. And so we are using this demand to find new ways of preserving food and actually also enhancing the packaging of this said food. And here in the table, we have some examples of essential oils that have already been used and impregnated inside films, plastic films, or bioplastic films, biopolymers actually, and been used in the industry. And how do these essential oils work? Basically, they are impregnated inside the packaging, and then can become volatile, and the headspace of a package will have these essential oils, the volatiles of these essential oils, that can have different functions, namely protection against UV light, induce or delay chemical reactions, reduce or promote microbial growth, and other bioactivities in terms of what can be food preservation. Still, essential oils pose quite some challenges, both in terms of the effect, the bad effects it can have on food and on the package itself. In terms of food, they can and they are known to promote odor and flavor changes. They are quite sensible to heat and light. They can promote color changes of the actual food, and in some cases, less food can be placed inside a package when protected with essential oils. Still, on the package, there can be some drawbacks, namely because of being impregnated inside the plastics or the papers of the packaging. The elasticity can be reduced, which in turn increases brittleness. In some cases, the thickness of the packaging has to be increased, and also sometimes transparency is reduced. For some types of food, transparency is not a problem, it's actually negligible, but foods like meat and fish, packed meat and fish, transparency is paramount. So these are some of the drawbacks that essential oils have been posing in recent years. So to overcome these drawbacks, nanoencapsulation, we found that it could be a viable and possible solution to overcome the drawbacks. So nanoencapsulation is when the active agent, in this case, the essential oil, is placed inside a membrane, and there is a controlled release of these volatiles, of these essential oils into the package. So this reduces most of the drawbacks of using essential oils, and in turn improves their biological activities. This controlled release is usually triggered by a stimuli, which can be mechanical effects, temperature fluctuations, changes in pH, biodegradation of the food, solubility of the medium, and also by diffusion. So when controlling these stimuli, we can control how the essential oils are released into the packaging. Then there is intelligent packaging, which is the next step in terms of active packaging. Active packaging, like I said, is when there is a promotion or there is an interaction between the food and the package. Intelligent packaging is when the packaging exactly becomes intelligent. So it is designed to monitor and communicate the information about the food quality and provide that information to consumers. These intelligent packages usually have mechanical, chemical, or electrical functions. Most of these packages are time temperature indicators, meaning if the temperature has been exceeded in certain foods, or it has been very low, if how long in terms of the shelf life has been passed on that food. We also have ripeness indicators, and most of this intelligent packaging relies on biosensors, and some of them even have electronic displays, but very few. So this biosensor is composed of a detection system, a signal processing system, and an electronic system. Basically, the sensor receives information in terms of a biological input, buildup of certain molecules or other stimuli, and then it's translated from a biological input into a digital signal, which is interpreted, and then a display is shown. So we have been working on combining these three technologies: active packaging, nanoencapsulation, and then biosensors, to actually extend the shelf life of foodstuffs. And we expect also to provide higher protection against oxidation of food. So when like I had explained, the steps of the biosensors, we are intending to reach when the signal is translated into a digital signal, a stimuli is given to the nanocapsules to start releasing the essential oils. So instead of immediately the display saying the food is not it's not safe to consume, we want the signal to be sent to the nanocapsules that will open and release the essential oils and extend the shelf life of the food product. So for that, we have been working on two projects. One of them, Bioma, is a project that has been studying all different types of plants and studying their essential oils, combining simple distillation or steam distillation, which is the classical method of obtaining essential oils, combining it with ultrasound, microwave, and Soxhlet extractions, so we can increase the yields of essential oils. We've been working with these species, which seem to be the most promising species. And then we are going to start a project which is Plant Pack, which will, of those species of plants, we will be detecting all the essential oils and all the volatiles by gas chromatography. And when we have the complete profile of these these plants, we will perform to preserve, to save some money and time. We will carry out in silico molecular docking, so we can understand how these molecules will inhibit oxidation enzymes, or even inhibit enzymes that are present in microbial life, which is usually contaminants, which are contaminants of food. So after this molecular docking, we will perform, knowing which are the most promising essential oils and molecules, we will perform response surface methodology to optimize the extraction of these molecules, confirm their bioactivities in vitro, and then we intend to produce two different types of technologies. Basically, one is preservation of packed food, like packed salads and other packed food, with pods containing volatile molecules that will, at a certain specific time, release the essential oils, the volatiles, which will preserve this salad. And also slice separators for sliced ham, cheese, and other foods, which will have their own specific essential oil that will release itself into the headspace of packaging. So we are working on the active packaging and essential oils, and eventually we will try and then join this with biosensors. And at the time, we will be looking for some collaborations to get the know-how in terms of this biosensors. So to wrap it up, we know that there is a need and a demand from consumers to change from synthetic and artificial molecules and packaging, or plastic packaging, if you may, into natural and sustainable packaging and sustainable food preserving additives. There are limitations. We are working with essential oils which have limitations. Some of them, most of those limitations can be overcome with nano-encapsulation. Biosensors are the most promising technology we have to reduce food waste, which is a growing concern. They can actually help and extend shelf life of foods. And we hope in the near future, the combination of active packaging, nano-encapsulation of essential oils, and biosensors could result in safer and higher quality of foods. So this is more or less what I had to say. It's what we've been doing in essential oils and what we expect to be doing in the near future with biosensors, and looking for some collaborations with anyone who would like to jump in. Thank you very much.
Thank you very much, Miguel, for a very nice talk and concern of all of us, I believe, in our everyday life. I'm just wondering, probably it was considered like to place inside of packaging some absorber, because mainly the most kind of dangerous effect coming from moisture inside of package. And this related to growth of fungi and, like different kind of things. Is it considered to put some absorber, like, for example, in technical life, we use some silica gel to absorb moisture in certain places where we don't need moisture to appear. What about the packaging?
Well, I don't think silica. I think silica is actually dangerous if eaten. So silica is, as an absorber, silica could not be used in food packaging. I'm thinking about meat, packed meat. Silica is not a solution, but yes, absorbers can be used to reduce moisture, which is one of the most, how can I say, one of the most important ingredients for microbial growth, especially fungi. So yes, absorbers are used, but silica could not be considered because it's harmful for consumption.
No, I use this as example. Of course,
yes, then yes.
It meant that it could be used in the products. So,
Yeah.
but probably some materials or even natural, some natural products can be used as an absorber and added to the packaging inside. But
Exactly.
also I noticed that recently they start to use some mixed packaging, like hard paper with plastic, like top plastic to see. But most like main part would be hard paper. So this probably also reduce the appearance of different products which we don't want to have.
Exactly.
Right. So just 1 second. I probably yes. So it's a question from Rocio Canavas. So it's thank you very much for a very interesting presentation. Which program are you going to use for modeling in silica? Thanks.
Oh, good question. We are going to use, we usually use two of them. We use Autodoc 4 and Autodoc Vina, which are, well, some of the most used programs for the docking studies. Those are the two we are going to use, Autodoc 4 and Autodoc Vina. In our research group, we have developed a program. Well, it's an operating system that performs the classification and the docking of hundreds of compounds sequentially, and we can do this with Autodoc Vina and Autodoc 4. So it will be those two programs using the MOLA operating system.
Okay, thank you very much. So I don't see any questions right now, but it could be appear during our open discussion. So thank you very much again for your interesting presentation. And so we are moving now to the last talk of this session. And the talk would be given by Amall Ramanathan, and the title of this talk is New Half-Metal Perovskite for spintronic sensing application. So I presume that the presenter is ready for the talk.
First of all, I'm Amall Ramanathan, and I'm a material science researcher, and I perform first principles calculations based on DFT codes, and I predict properties for new materials that could be very desirable before we can do an experimental investigation. So I'm very, very happy, of course, first of all, and I'm thankful to all of you, the organizers of CSIC 2021 and MDPI for inviting me and giving me this opportunity to present my work. This is actually the most recent work for me done at the Computational Physics Lab in the University of Jordan. And what I found from feedback was that people were saying that it's a little bit technical. So I've made the presentation very, very simple to keep also to the time and to just give a feel for the work. So first of all, you're seeing now the outline, and I've just touched briefly upon spintronics, what it is and why do we need it, then the materials, then perovskites, then half metals, and finally, of course, the last three are basically the work, which is the method of calculation and the results that have been obtained, and the conclusions. So As we all know that instead of now in today's world where we are having such a lot of advancement in science and technology, and we need fast data transfer, and response time should be quite quick. So instead of going and sticking to old-fashioned electronics, which is based on charges, we would like to carry all the information on the electron spin. Of course, the advantages, as we are seeing here, would be a very high data speed with low energy loss compared to conventional electronics. And of course, we would have miniaturization possible. And of course, this whole thing about the spintronics would be compatible with conventional electronics more than the other parallel technologies which are being explored, like molecular electronics and quantum technology and so on. So spintronics has its good advantages. So, but the disadvantage is that it's just very, very much in the beginning, and mainly we are seeing work that is theoretical or predicted, and actual fabrication of devices and using of materials, we face a lot of challenges. So like you could say how to detect the charge, or how to detect, how to detect the spin or the orientation, and how to transport this effectively over long distances. All this would be challenges that would be need to address. Briefly, I would like to just tell you a little bit about the spintronic materials that are broadly categorized as the magnetic metals. And then we have the topological insulators, and then we have magnetic semiconductors. These are the main broad categories. In magnetic materials, we would be having the ferromagnetic metals, and we would be, of course, the magnetic metals, I'm sorry. So we have half metals also in this. And actually, I would like to focus on the half metal because this is what I'm interested in my work. The topological, of course, are based on organic or inorganic compounds or systems. Then we have the magnetic semiconductors, which could be a half semiconductor or the spin gapless semiconductors. So now let's just go back to the little bit about perovskites. About I think in the 19th century or so, so about 2 centuries back, we had this a Russian scientist or Russian mineralogist who discovered this mineral calcium titanate, yes, which was having a special structure which they named after him, and they called it perovskite. So nowadays, this perovskite has been very, very attractive to the people because a lot of materials that can have the same structure or crystal structure of calcium titanate, namely the ABX3, where you have the A is a cation and B is a cation, and X is an anion, which could be a halogen atom or an oxide atom. This structure similar to calcium titanate is called the perovskite structure, and we find that a lot of very good electronic properties and have been found for these type of materials. And the good part about is that you could just use all the chemical elements present in the periodic table to make combinations, and you can do like mix and match and try to get exotic properties. And of course, the band gap would change depending on the chemical composition and functionalization. So this is a very vast field, and it has gained its popularity in the last few years based on its applications in solar cell, because it has a lot of good absorption capabilities in the solar spectrum, visible solar spectrum. So what I wanted to do in this work was to explore a perovskite structure that would also at the same time be like a half metal, in order to see, because there have been a lot of also studies recently, people are very interested in half metals, because these you can have where you have two spin channels basically in the half metal, where one would be having a semiconductor or an insulator type of nature, and the other would be metallic. So this can give you like you can have spin only in one direction being made possible. So this is like you could have 100% polarization, only up spin, all up spins, or all down spins. So depending on the material that's being used. So these, once you have a spintronic material is half metal, that is a spintronic excellent, one of the excellent spintronic materials, you could use it to inject spin into systems or create a valve which controls, or controlling the control system. You can have a spin control. You could have filters that filter, and all kinds of other devices. So now I want to go into what my details about the methodology that I've used in order to characterize this perovskite, namely the niobium scandate. Niobium scandate, as yours, is a transition metal perovskite, and I've used this full potential linearized augmented plane wave method, which is there in the Win2K program software. And I've done spin polarized calculations with generalized gradient approximation for the exchange and correlation based on the papers or article due to Perdue, Brook, and Rezanoff at a K-point mesh of 10-10-10 for optimizing the lattice constant and finding the ground state energy. Once this was being done, performed more accurate calculations, we're using the MBJ, or the modified Johnson's exchange correlation due to Blaha, and they used a 15-15 by 15 K-point grid for the electronic and magnetic properties. Now, of course, the convergence threshold has been kept very low, and 10 to the power of -4 Rydbergs for energy, 10 to the power -4 for electron charges when we want to do the calculations. Now, here is the structure. Unlike the recent structures that have been used for transition metal perovskites, where usually, as you are seeing, the corner atoms. Okay, so what I have done actually is use the cubic structure for the perovskite. And in the cubic structure, the corner atoms are the transition metal niobium, unlike in other studies where the transition metal usually occupies the B site or the center of the cube, body center of the cube. So the oxygen atoms are, of course, sitting on the face centers, as you are seeing. And upon optimization, I obtained a lattice constant of 3.985 angstroms. And this was put into the structure file, and all the calculations were done, based on this lattice constant value. Now, in this, the band structure that we are seeing here, I didn't put in the GGA. I've done both for the GGA, or the generalized gradient approximation, as well as the MBJ. But what I can just say here is that when I used the MBJ, I found that the band gap opened up, and instead of being a half metal as it was with the GGA, it became a metallic semiconductor. But of course, in both the spin up and the spin down. So here what we are having, the spin down is on your left-hand side, and you are having on the right-hand side the spin up band structure. What we can see from here that, of course, the band gap is now opened up and become bigger in the spin down or the minority case, and we are having around 2, I'm not seeing the value, but I can just give you the value. I think 2.03 electron volts is the band gap, and if I remember right, for the GGA it was around 1.6 or something, so it's become a bigger value, opened up more. And of course the spin up was fully metallic in the case of the GGA, but when I used this more accurate exchange correlation of modified Beckett-Johnsons, I got it to be a semiconductor with a very small band gap of 0.7 electron volts in the spin up also. So this is basically now, and we can say that this niobium scandate is a metallic semiconductor. We cannot call it a half metal anymore due to these values. So we could see now, we can show the values for the band gap here, and here, of course, it was not 1.6, it was 1.8, my mistake, in the spin down. And then, of course, we are having in also the K point values, the gamma to gamma has changed to an R to gamma gap. And of course, the new gap is opened at X gamma, where you're having 0.78. Also in this, on the last column, I have put the half metal gap, not the band gap, but the half metal gap, which is actually the spin flip energy, which is now you can see in the case of GGA, it is 1.554 or 55, you can say, electron volts, which is for the energy required for electrons to jump from and do a spin from the minimum. That's the minimum energy required, of course. So for the minority spin electron to go from the valence band maximum to the Fermi level of the majority spin. So this is the energy that we call the energy half metal gap energy. So here in the case of MBJ, we are having about around 1 electron volt, and this is substantial. So for good spintronic materials, we need to have a large band gap, and that's the case here. And we need to have a large and substantial half metal gap too, for robustness of the device. So these results are very encouraging. In this, I have shown the total density of states and the partial density of states for the different constituents. So in the first graph, on the first top part, left top one, we have all the total density of states for all the elements. And you are seeing basically the gap, which is there, where you're seeing near the Fermi energy, that's the line over there. I don't know, can I use the cursor? Yeah, okay. So you are having this line here. This line is the Fermi level, exactly sitting around at the Fermi level. We are having these the spin up thing, showing that it's very close to the band Fermi. The band edge is very close to the Fermi level there. And here, this is giving an indication of the gap in the spin up or majority channel, and in the minority, we are having the wider gap. I think this is the first one is the is the niobium, and this one is the scandium, obviously, because as my results showed, that this is hardly doing any, there is very negligible contribution from scandium. And then we are having the oxygen. So this is the first one is a total. This is the partial atom ones is the niobium, the transition metal is on the right corner. And since you're seeing it, you all will appreciate much better than me at this moment. Of course, I've already done the results, and I remember that this one and the niobium is contributing the D bands, because if I wanted to see the legend and to show you that the D bands are the maximum contribution from the niobium D bands. Then we are having here, of course, the oxygen. So mainly the niobium and the oxygen are contributing for the density of states. In the oxygen, we have the p orbitals, the py and the px orbitals that are contributing the for the density of states. Here we can see on the table actually the magnetic moments. Yes. So if anybody did not get the density of states clearly, the picture, we can see it here in actual values. So the niobium magnetic moment is 1.85. And we are having scandium is 0.01, which is very, very small. And the oxygen here is very small also, 0.07. This is with the GGA results. The interstitial, which is getting out of the, in the interstitial space, we are having also 0.36 magnetic moment, and the total moment, which we are very much interested in, and it should be an half metal value. For a half metal should be an integer value is 2. With MBJ, we are having here again the same, approximately the same things, and we are seeing that we can confirm that it is mainly a half metal and a magnetic semiconductor. So in conclusion, we are having the full potential investigation using the linearized augmented plane waves for the perovskite niobium scandate, and we have predicted it to be a half metal and an intrinsic semiconductor in both these exchange potentials respectively. Of course, the size of the band gap being, as you're seeing, around 2 in both cases, and 1.8 and 2 is good for the feasibility of it being used in spintronic applications. Of course, also we are, as I mentioned earlier, the half metal gap is also good, and we do not have any problems with this being good for applications in spintronics. So, but the main problem with this work would be that I do not have any experimental validification or experimental calculations or work done by other scientists that could collaborate and make this more interesting to the scientific community, and then people could think about devices that could depend on niobium scandate. I thank you all for your attention, and if anybody is interested in asking any question, it will be my pleasure to answer.
Thank you, Amall, for interesting presentation. And the only question I can ask, I don't see any question at this moment. My question is just in comparison with other perovskite materials, how this particular one is standing from the point of view of application, and of course, like half metal energy value and other parameters which you calculated during your work.
I think it is standing good because you see although I have not put in, I did it a little bit later. I have, since I found the initial prediction and values good, I did go in to do the, address the stability and the thermodynamic stability by doing the formation energy calculations. And I found that, yes, it is feasible and it could be made in the lab because it's around 2 Rydberg per formula unit. That's around 27 electron volts per formula. Yeah.
Okay. Thank you very much again. I believe I don't see any other question. So I'm now passing chairing to Professor Nicole. Please,
Yes.
for final remarks.
Ladies and gentlemen, it is my honor to present you the closing ceremony for the first International Electronic Conference on Chemical Sensor and Analytical Chemistry. I am from Université of Lyon in France. So this conference was structured according to different sessions: analytical methods, instrumentation and miniaturization, biosensor, electrochemical devices and sensors, gas sensors, materials for chemical sensing, optical chemical sensor, general presentation were also possible. And there were 192 submissions, and 124 were accepted as poster presentation and proceeding. And the origins of this contribution mainly from 27 countries, from Spain, 22%, from Italy, 14%, from Germany, 11.4% from Portugal, 10.4% from Romania, 10.4%, and from Canada, 9.8%. So the session chair were Professor Manel Del Valle from Spain and Professor Huangchuanzhu from Nanjing University in China, Professor Núria Serrano from Université of Barcelona in Spain, and Professor Giovanni Neri from Messina University in Italy, Professor Giovanni, it was a mistake, it is our colleague, Professor Comini from University of Brescia, and Professor Dr. Elena Benita Peña from Complutense University of Spain. So this session chair selected the papers, and I thank them very much. Yes, so during the live session, you were able to listen for 6 keynote speakers, Professor Benoît Piro and Professor Elisabetta Comini from this live session. And from the previous live session, you were able to listen Professor Kourosh Kalantarzadeh from Australia, Dr. Michele Penze from Italy, Professor Arkady Zhukov from Spain, and Professor Huangchuanzhu from China. And also you were able to listen invited speakers, Dr. Ren Zhang from Australia, Dr. Andrei Bratov from Spain, and Dr. Amir Atami from Sweden, and also 9 selected speakers. So during this conference, several conference awards will be offered: the Best Contribution Award, the Best Presentation Award, and the Best Poster Award. Unfortunately, at the moment, I am not able to present the winners. Sorry, the selection is not completed. So the selected paper from the first International Electronic Conference on Chemical Sensor Analytical Chemistry will be published or will be submitted in a special issue. I will be the guest editor. So you are invited to submit your paper in this special issue. I show you here the website address. And I thank you for attending this CSIC conference. And thank you for your attention. Okay, thank you, Tatiana.
Thank you. Thank you.
For sharing the live session.
Yeah. Right.
And thank you, Anna.
Thank you for participation in this session.
Yes.
Okay.
All the best to everyone. Bye. Bye.
Thank you very much.
Bye.